Organic Chemistry, Chem 213, Exam 5 Material, Part 1. Amines. Amines are organic nitrogen compounds. They are derivatives of ammonia. The nitrogen atom has a lone pair of electrons, making amines both basic and nucleophilic. Amines occur naturally in plants and animals. Here are 3 examples of compounds that not only contain amines, but other functional groups you've already seen. Classifying amines. We're going to classify amines just the same way that we classified carbons earlier and we classified alcohols earlier. How many R groups are directly attached to the nitrogen? Amines can be alkyl substituted or aryl substituted. The nitrogen, again, it has its lone pair of electrons. It's sp3 hybridized, pyramidal, and nearly tetrahedral. We're going to classify them as primary, secondary, tertiary, and then quaternary ammonium salts. Those are going to be a little bit different than just plain quaternary. Let's take a closer look. Ammonia, nitrogen with 3 hydrogens on it, is not classified as an amine. It is ammonia. In fact, it's not even an organic compound yet. Now, replacing one of those hydrogens with just 1 carbon, now we have our organic compound. Here we have our nitrogen. It has 1 R group. It would be a primary amine. These structures show the hydrogens and R groups drawn explicitly. Normally, you'd be seeing amines the way I have them up here in the condensed structural formula. 2 R groups, secondary amine, 3 R groups, tertiary amine, and 4 R groups with a positive sign on the nitrogen because its formal charge would be a +1. And this does say quaternary ammonium salt. So typically when we do have our quaternary ammonium salt, there needs to be with it its anion. So why don't you add to your notes an X minus. For this class, we're pretty much going to be having halogens as our anion, but it could be any anion. IUPAC names, simple amines. What we're going to see with amines, there's actually a lot of acceptable ways to name amines. This is the first way we're going to look at, simple amines. This is done by adding the suffix amine to the name of the alkyl substituent. Tert-butylamine, we have our amine right here, and this group, what we have in black right here, this is our tert-butyl or T-butyl group that we learned as a common name earlier. Here's one way that we can name a ring structure, cyclohexylamine. Again, this is giving amine the priority. And you would be using these simple names when you didn't have any other functional groups present also on there that would have higher priority. 1,4-butane diamine. Notice that the E is retained in butane when we have our multiplier di, di in front of the amine. The di is telling us we have 2 amine groups. The 1 and the 4, they're telling us that they're on carbon 1 and 4 of our butane. The suffix amine can be used in place of the final E in the name of the parent compound. So here we have a situation where they kept the hex N, so cyclohexane. They took off the E here and put amine. Now on the previous example up here where they had diamine, they kept the E because they're the multiplier following it. Here they don't keep the E. We saw in the previous example when we had a diamine, but what if we have 2 of the substituents? Well, symmetrical amines are named by using the prefix di and tri before that. Again, this is simple amines. Problem, write the structure for the following and classify them as primary, secondary, or tertiary amine. At this point, I'd like you to go ahead and pause the video, draw the structures, and come back and see how you did. Methylamine. It only has 1 R group. Nitrogen needs to have 3 bonds. That's why it gets 2 hydrogens. Methylamine. Triethylamine. It has 3 ethyl groups. Here's an example where we had the ethyl drawn first in the condensed structural formula and then the nitrogen. This is also an acceptable way to show that. Or you could show them explicitly. There's other ways you can draw these structures. Isopropyl, something coming off carbon number 2 in this case, it's our amine. Diphenylamine. We have 2 phenyl groups coming off our amine, and it needs one hydrogen. Again, nitrogen has 3 bonds total. All right, now that we've named them, let's classify them. Methylamine. This nitrogen has 1 R group on it. It's a primary amine. Triethylamine. 3 R groups. It's a tertiary amine. Isopropylamine. Remember, it's the nitrogen only that we want to know how many R groups are coming off of that. This nitrogen has 1 R group. It's a primary amine. Diphenylamine. Here's our nitrogen, 2 R groups, secondary amine. For nomenclature, when nitrogen does not have priority, amino is used as a substituent on the parent molecule. Problem: draw the structure for the following and classify them as primary, secondary, or a tertiary amine. Go ahead and pause the video, come on back, and see how you do. So here we have butanoic acid. It's on the top of the nomenclature list. It has priority. The amino group does not. This is a butanoic acid, and coming off carbon number 2 is our amino group. Here we have a benzoic acid, and it's telling us we have 2 amino groups coming off carbons 2 and 4. 2-butanone, that's a ketone. Ketones have priority over the amino group. This 2, because ketones have priority, we need to give the ketone feature the lowest number, and by default on this structure, amino is number 4. Para-aminobenzaldehyde. And we also see here aldehydes have priority over amino groups. And since this is on a benzene ring, we can use the orthoparameta system. And in this case, this happens to be a para. How'd you do? Classifying the structures. This nitrogen has 1 R group. It's a primary amine. Here we have 2 nitrogens, and they're both primary amines. 4-amino-2-butanone, that's also a primary amine. And para-aminobenzaldehyde, that's also a primary amine. Naming amino groups that have multiple or different alkyl groups, they can be named as an N-substituted amine. The largest alkyl group gets to be the parent, and the other alkyl groups get to be the N-substituents. Here we have a nitrogen with 3 R groups, so this is a tertiary amine. And you can see that this group over here has more carbons than the other 2 R groups. This one has 1, 2, 3. So this nitrogen with these 3 carbons get to be the parent name. That gets to be propylamine. Now these other 2 groups, notice they're not coming off carbons. They're literally attached to a nitrogen. So we don't give them a number to tell us where they are coming off of carbon. That's what we've done all along so far. What we do is we give them the address capital N, meaning they are directly attached to the nitrogen. So these capital N's are addresses, just like our numbers were addresses. So we treat them the same way. The notation is the same. If you have more than one N listed, you separate them by a comma, and you separate the address, in this case N, from the name of it by a dash. They're treated just like we did the numbers. Another thing I want to point out is the most number of N addresses, the most amount of N addresses you can ever have on a compound would be 2. One of them, even if you have a tertiary compound, because one of them is going to be part of the parent chain. That's part of the name here, propylamine. If we have a tertiary amine, then we'd have 2 N's, and if we had a secondary amine, you'd only have 1. So the most times you can list the letter N for an address would be twice. Here we have nitrogen, and in this case you can see its parent group, the biggest, happens to include this ring. That would be a cyclohexylamine. The ethyl group and the methyl group are on the nitrogen, and they're still listed alphabetically. Notice ethyl comes before methyl, and we have the address capital N. It must be a capital N, meaning nitrogen. We have ethyl on our nitrogen and methyl on our nitrogen. So on this slide, either I gave you the name and I want you to draw the structure, or the structure and I want you to generate the name. And when we're all done with that, we'll come back and classify them as primary, secondary, or tertiary. Go ahead and pause the video and come back and see how you did. All right, with this one, we have our nitrogen here. And looking to the right of it, I have 2 carbons. On the top, I have 3 carbons. So this piece here gets to be my parent. And because it's coming off of carbon number 2, it would be 2-propylamine. Now remember, earlier we used isopropyl, and that was the common way or the simpler way of naming. So now we're going to be in the IUPAC system. When we use the letter N, we're going to use the 2, indicating it's coming off carbon number 2. So we have our 2-propylamine, and coming off of our nitrogen is an ethyl group. N-ethyl 2-propylamine. N-N-diethyl cyclohexylamine. Here's our parent piece, cyclohexylamine. We would have a 6-membered ring and nitrogen coming off of the ring. And we have 2 of the same group, ethyls, so you can write them above, below, or even to the right. N-N-diethyl cyclohexylamine. So the next one has 2 names, and that's because we have a common name in our ring structure. So this one can have 2 names that are acceptable, N-methylphenylamine or N-methylaniline. Let's take a look at its structure. Either of these 2 names would be acceptable. When we have a nitrogen on a benzene ring, that's known as an aniline, and we also have a methyl group coming off the nitrogen, N-methylphenylamine or N-methylaniline. For this last one, here's our nitrogen. We have 3 R groups coming off of it. The largest R group would be this group here, so this is our parent. The nitrogen is coming off carbon number 2. N-N-dimethyl 2-propylamine. Classifying. This nitrogen has 2 R groups. It's a secondary amine. This nitrogen right here has 3 R groups. Tertiary amine. The nitrogen here on N-ethylphenylamine, 2 R groups. Secondary amine. And our last one, N-N-dimethyl 2-propylamine, has 3 R groups. Tertiary amine. Quaternary ammonium salts. To name these, you name the R group, then add the ammonium halide ending. With a quaternary ammonium salt, all R's can be hydrogen. Well, that's a little misleading. If all the R's were hydrogen, then we would have ammonium ion, and that's not an organic compound. So in the sense it isn't all R's, you need to have at least one of these being a carbon. When you have your quaternary ammonium salt, be careful when you draw it that you make sure that the positive sign is close to the nitrogen. You might need to make your bond line to one of your R groups maybe exaggerate it a little longer to get it out of the way, so it's clear that it's your nitrogen that has the positive charge. And then your anion needs to have a negative charge, and it needs to be in the area of it, but it's not actually covalently bonded, so it's ionic bonded, so it's going to be in the area of it. For OCHEM, we typically have, with our quaternary ammonium salts, we tend to use the halogens quite a bit, but keep in mind any of the anions could be there. So the smallest of our quaternary ammonium salts would be methyl ammonium bromide. So you can see the name ammonium bromide, and what goes in front of the ammonium without a space would be whatever R groups you have on there. There is a space after the word ammonium and before the name of our anion, in this case, bromide. The compound itself does not need to be written expanded. The structure I have in the box here is the exact same structure, methyl ammonium bromide, that I have above it, and that's probably the way you're going to see these structures a lot more often anyway. Problem: draw the structure of the following. Go ahead and pause the video and come back and see how you did. Methyl ammonium chloride. It has 1 R group, 1 methyl group. So it needs 3 hydrogens to keep the 4 bonds to nitrogen, positive charge next to that nitrogen, and the chloride with a negative charge. Ethyl trimethyl ammonium bromide. I have 3 of the same group, the methyl group. So I went ahead and put them in parentheses and then said 3. I have my ethyl also attached. It has 4 pieces to it. I put my positive charge on my nitrogen and my bromide with its negative charge. N-methylpyridinium iodide. I like this example because I wanted you to know that even those common names that we saw earlier when we learned about the amines and the nitrogens in the heterocyclic rings, that they can also be part of our quaternary ammonium salts. So here's an example of what would happen. We have a 4th bond to our nitrogen. It has a positive charge, and in this case I have iodine off to the side. And the minus charge didn't show up so well, so I added a minus charge. So this is just a over-exaggerated negative charge next to my iodine. Benzyl trimethyl ammonium iodide. Here's our benzyl group. Learn that back in the benzene section. 3 methyl groups, positive charge on nitrogen, negative charge on iodine. So here's a poster I found from Compound Interest. This is compoundchem.com. I wanted to find out a little bit more about amines and quaternary ammonium salts, and on their site I found something I thought was interesting is this is a brief summary of disinfectants and antiseptics. Take a look on the right hand side over here. Diamines, so mainly used for topical treatment of wounds, and you can see a structure of a diamine here that's used for that. And on the bottom right, quaternary ammonium salts used in many antiseptic creams and kitchen surface cleaners. I thought this was just a little interesting to look at. So of course, this information is not on the exam, but I wanted to go ahead and bring in some functional groups you've already seen and maybe a little bit of interest to this so you can see where these are used in your everyday life. Diamines contains 2 amino groups. So we did see this at the very beginning of this section, and I want to go into it just a little bit more. So one of the first things I need to do is let you know that a CH2 group is known as a methylene group. This is something we could have learned a long time ago because we even had methylene groups back when we had butane. But we don't like to necessarily show you the name methylene right away because it could be confusing. We have a Y in there and an E in there, and it doesn't have a triple bond or a double bond. Know that a CH2 group alone is called a methylene group. So why do I bring it up now? Because we use the name methylene when we name some of these diamines. Now we're going to look at some specific diamines where each end of our carbon chain have nitrogen on there. These are the ones we're going to concentrate on at this point. So let's take a look at this one we have here. I have a nitrogen on the end. I have 4 methylene groups and another nitrogen on the other end. The name of this compound is tetramethylene diamine. That would be its common name. And the common name is used quite a bit, so that's why I want to go over some of these common names for you. Tetramethylene diamine. Now, its IUPAC name, and we did see this earlier, it's the same structure, is 1,4-butane diamine. The E is retained when you have a multiplier following it. And this name is telling us that the amine is on carbon 1 and 4 of 4 of them. Now it has a common name, putrescine. That's the part I think is interesting. Putrescine, just like you would think, does not smell very good. And in fact, in a couple of slides from now, I'm going to go more into putrescine. So hold off on that for just a minute. I wanted to give you a little more information on that. Let's take a look at the next name, and you'll see why I'm rushing to the next name in just a second here. Cadaverine. We have 5 carbons here instead of 4, and its common name is cadaverine. So I'll have some information on putrescine and cadaverine a couple slides from now, so I hope I piqued your interest in that, but let's look at nomenclature first. All right, we have a blank here because I would like you to fill in the blank. So there's a prefix that has to go here, methylene diamine. How many methylene groups do we have? And what's the prefix for 5? Pentamethylene diamine. Its IUPAC name would be 1,5-pentane diamine, and again, its common name is cadaverine. Practicing writing the IUPAC name this time, and this compound does not have a fun name like putrescine or cadaverine, so we don't get to talk about that one. But let's look at how would you name. You have the 2 nitrogen groups and you have 6 methylene groups. How would you name this using the IUPAC system with the numbers? 1,6-hexane diamine. Amines that contain 2 amino acid groups. Diamines are used to prepare polyamides, also known as nylon, polyamides, and polyureas, also known as spandex. We did get to see part of this reaction in an earlier section. I wanted to go ahead and revisit this because we are talking about the diamines, and I want you to see it from the diamine point of view. Here is a reaction of nylon synthesis. Nylon 66 is one of the most common nylons, and sometimes they'll call it nylon 6,6 or just the number 66. Let's take a look at the reactants. You have the dipeptic acid here, and we have on this side here, we have a carboxylic acid. Over here, another carboxylic acid. The total number of carbons in this reactant would be 1, 2, 3, 4, 5, 6. And that's where the first 6 in nylon 66 comes from. The second reactant is our hexane or a hexamethylene diamine. And here we go. This isn't a carbon. Here's where the carbons start. 1, 2, 3, 4, 5, 6. This has 6 carbons in it, and that's where the second 6 comes from. These 2 pieces come together, and these start forming the polymers. This is one of those step growth polymers we've talked about again in a previous section. So this is nylon synthesis, and then I was curious about spandex. They talked about polyureas, and this is a monomer of spandex, and it shows us that this section through here is the soft rubbery part that gives spandex its elasticity, and this is the rigid segment. So I offer this slide to you as an interest slide. You are not going to be responsible to write out the reactions of this or write out the monomers of this. Again, I wanted to show you some real-life examples of nitrogen. Now, making nylon is really interesting, and there's a whole bunch of videos online, so I'm offering 2 of them to you here. If you are watching the recorded video of me talking to you, you can't press the button and have this play. But if you're looking at this from the PowerPoint instructor version, you can go ahead and just press play. What happens with nylon? And I'm up here at this drawing here. It says how to make nylon plastic chemistry. Take a look at this beaker here. What happens when you make nylon? There's actually 2 different phases. You have your organic phase and you have your aqueous phase. And there's a surface in between the 2 of them. And that surface is where the interaction happens and the reaction happens. And that's where the nylon is made. So they're drawing the nylon out from that. If you want to learn more about how nylon is made, the top video explains the chemistry extremely well. If you want to be entertained, then the second video, you want to watch this one anyway. The Crazy Russian Hacker. The guy is so funny. So he goes ahead and makes nylon too. So if you want to take a look at that. As promised, a little more information on putrescine and cadaverine. They are both produced by the breakdown of amino acids in living and dead organisms and are both toxic in large doses. It's also known as the odor of death. So when we have rotting material, that's what's given off. That's the smell that's given off. The breakdown gives us both the compounds putrescine and cadaverine. The difference in their structures are derived from their biological sources. Cadaverine comes from removing the carboxylic acid group from the amino acid lysine, whereas putrescine is derived from a different amino acid, arginine. Arginine is first transformed to ornithine, which is a key part of the urea cycle that allows the body to get rid of excess nitrogen. Some of that ornithine then ends up as putrescine, and it is through routes like that that cadaverine and putrescine contribute in small parts to the smell of urine. Okay, so the names make sense. The things smell. Now, here's what I have a question with. We saw earlier that they use the other one with the 6 carbons, the 6 methylene groups, as making nylon. Well, this is what gets me. Somebody had the idea to say, hey, let's make nylon out of putrescine. Well, first of all, someone had to say, I'll do it. That stuff has got to smell. And they have made nylon out of putrescine. In fact, putrescine is reacted and it makes nylon 4,6. Oh, I might have made a mistake here. I think the first 4 has to do with the hexamine and then the second one with the acid. So switch that on the previous slide. And this is marketed under the trade name Stanol. This is the monomer for Stanol. Here's some examples of things I found made by Stanol. This happens to be components for computers, but they also take the nylon 46 and they make it into fibers, and they can make it into clothing and other things like that. So something kind of interesting about putrescine and cadaverine.